Yeah. So good morning, and we will start today's session. Today we will look at DFS, the depth first search. I'll do a brief summary of what we did in the last class, and then we will see how to implement a depth first search. I'm going to use Geek for Geeks code, but we are going to understand that code very closely, and so that you can write your own code and make it happen. Okay. So let us just understand how to write DFS. I think I had given you a explanation of DFS in an earlier session, but nevertheless, let's do a brief recap and then start. Okay, so yeah, so this is what we know about DFS. DFS stands for depth first search. So if you're given a graph something like this, so I'll arbitrarily call this as 1. Okay, let's represent this as 1. This is, let's call this 2, 3, 4, 5, 6, let's say 7, 8, 9, 10, 11. Okay, so there are 11 nodes in this graph. So if you do a depth first search starting at 1, okay, let's say we start at 1. How do you do depth first search? We have to first find out who are the neighbors of 1. That is typically coming from a adjacency list or a adjacency graph. Adjacency list or adjacency matrix. So you have 1. What are the neighbors of 1? So the way it would be represented is, let's talk a little bit about the representation. If it is an adjacency list, then against 1, we will have a list of neighbors who are neighbors of 1. So they are neighbors of 1 are 2 and 7. It's an undirected graph, so it doesn't matter which way it is going. So 2 and 7 are the neighbors of this. So if we represent this, if you look at the representation of this, let's say 2. Who are the neighbors of 2? The neighbors of 2 are 1 and 3 and 4. So the neighbors are 1, 3 and 4. I'm just representing it first. Then who are the neighbors of 3? Neighbors of 3 are going to be 5 and 2. So 5, or you can say 2 and 5. Okay. Neighbors of 4 are only 2. Okay. And this goes on and nothing. Okay. So I'm not going to write for everyone, but I think you know this is what is my adjacency list, which is a more common data structure than adjacency graph, adjacency matrix, adjacency list, okay, which says that for every node in the graph, who are its neighbors? This is represented as a list, okay, and we are going to understand today in C++ how we do this. So this is a list. This is a list. So like that, for each of the nodes, there is a list against that maintained, which records who are the neighbors. Okay. So this is how this tree will look like. This will of course go into 5, 6, 7, 8, but this is what it will do. So when I do a DFS traversal starting at 1, how it will happen? So I'll go to 1. Okay, I'm starting at 1. I'm done 1. So I'll mark 1 as visited because I don't want to go back again. I don't want to go in cycles. Visited of 1, whatever way you want to record it, visited of 1 will be equal to 1, which was initially 0. That is because I visited that node. So I am getting visited of 1 equal to 1. Okay. Then I find out who are the neighbors of 1. So I am finding out 2. So now I pick one neighbor. I don't look at the other neighbor right away. I don't even look at this neighbor till I am done with this neighbor. So I go to 2. Then I find out 2. What are the neighbors of 2? The neighbors of 2 are 3 and 4. Neighbors of 2 are 3 and 4, yes, and 1. So I go to 2. I see these are the neighbors 1, 3, and 4. Now, should I go to 1? No, I don't want to go to 1 because I cannot go to 1 because 1 is already visited. I have to go to the neighbors who are not visited of 2, which are not visited, and 2 is the neighbor of 1. So I should, of course, print 2 here on the screen. Okay, so I printed 2. Is there some problem?
No.
People are able to see now. So I print 1, then I print 2. Then who are the neighbors of 2? We saw 1, 3, 4, out of which 1 is already visited, so I don't visit it. What is the other neighbor of 2? 3. So I now 3. I ignore 4 for the moment, just like I ignored 7 at this stage. I go with 3. Now, who are the neighbors of 3? 3 has 2 neighbors, 2 and 5. So I don't go to 2 at all because 2 is already marked as visited. So visited is 2. So visited, because I went to 2, right? Visited 2 is 2, okay, is equal to 1. And what am I seeing on the screen? I am seeing 1 and 2, and I am seeing 3. 3 is also marked as visited because I went to 3. Visited 3 equal to 1. The moment I visit a node, I do it. So 3 neighbors are 2 and 5. Okay. So 2 is already visited, so I go to 5. Okay. I go to 5 and mark 5 as visited. And now I am not going to draw it here. So visited 5 also equal to 1. Now I am focusing on 5. What are the neighbors of 5? The neighbors of 5 are 3 and 6. 3 is already visited. It's already visited. So I can't go to 3. So I go to 6. So 6. Now, does 6 have, so I say visited 6 equal to 1. Okay. Okay. Now, I have gone to 6. Now, so my output is 1, 2, 3, 5, 6. This is my output. Okay. And now, how do I proceed? So, now 6 is done. So, there is no point doing, and 6 has no other neighbor other than 5. So, I go back to 5. Okay, now just like a stack, I pop 5. So because that was an earlier neighbor which I had not visited, which I had visited 5. So I go to 5. I check for the neighbors of 5. There are 3 and 6. Is there any neighbor remaining? No. 3 is already visited. 6 are already visited. There are no unvisited neighbors of 5. So I go back. So it pop 5 also. So now it is 3. Okay. So when I say 3. What will happen? Yeah. So 3 has what neighbors? 2 and 5. So are any of them unvisited? No. So I pop 3 also. It doesn't matter what I pop. So now I go to 2. Are there any neighbors of 2 which are unvisited? Yes. 4 is unvisited. So I then do 4. Now I go to 4. Does 4 have neighbors which are unvisited? No. So this is not going to happen. So I am done with 2. And now I pop 2. So now the journey for 2 is over. So I go to the first. So this 1 is still incomplete. 2 and all are over. So I now look at who is the other neighbor of 1. It is 7. So I go to 7. So now 7 I marked as visited. I am not bothering to do that. So 7. Next data is 7. 7's neighbors are 1 and 8. So 1 is already visited. So the only guy I can go to is 8. So I go to 8. 8's neighbors are 9 and 10. So which are unvisited. Also 7 is there, but it's visited already. So 8 is also marked as visited. So I look at 9. Is 9 visited? No. So 8's neighbors are 9 and 10. So I can do 9. Now I go on to 9. 9, does it have, 9 is visited now. Does 9 have a neighbor which is unvisited? No. So there's nothing more to do on 9. So I go back to 8, pop 8. No, not pop 8 yet. I have to still work with 10, which is the other neighbor of 8. So I finished with 9, so I pop 9 and I go to 10. Why do I go to 10? Because that's the other neighbor of 8 which is waiting. So I go to 10. Then I print 10 as visited. Does 10 have another neighbor which is not visited? Yes, it has 11. So I get 11. And 11 is visited. 10 is completely visited, so there is no more. So this is the order in which I would get the output. This is one of the order. It could also be, he can go this way also. So there are not one definite order. It can be 1, 7 also and then go forward. Okay, it can be 1, 2 also and then go forward. Here also When you are at 2, you can either choose 3 or 4 because both are neighbors. So there is multiple ways this tree can come as output in a DFS search. Only thing that is guaranteed is everybody is searched. So this is a depth first traversal. Okay. Pretty easy. It is similar to our pre-order, post-order, but follows a specific order of traversal. Okay. So I think this much is clear to everyone. Can we assume that this is clear so that we look at the code? I don't know. We'll let you know today if it is possible, Arjuna. Okay. Arjuna is taking a little while because a lot of our staff is down with COVID. Okay. It's clear? So now I am going to show you some code. Okay. It's there on Geek for Geeks. And then I'm going to talk about, you read the code for 5-10 minutes. Then we are going to discuss that code together. Okay. So, and see whether you make sense. Okay. So, I'm going to go DFS Geek for Geeks. No, you can show DFS Geek. So this is the link. Go. Let them see. No, Baba, the link is clear. So that is the link. Okay. So we can even paste the link there. Okay. We are pasting a link there. Please go there. And after going to that link, I'll show you what to do. Okay. No, the link is above. Okay, go to the implementation of DFS. You can read it if you want, but not needed. Try and understand this code. Okay, so I'm going to give you about 10 minutes to understand this code. Maybe at 12 o'clock, we will start talking about this code. Please take this time, try and understand, because there are some data structures you might not have seen or you might have seen. There is a map there, there is a list there, so try and make sense out of it, try to do some reading. And at 12 we will start talking about this program. It's a good program and it tells you how to use some data structures and also how to do DFS. Now, for all our coding, DFS is like bread and butter. So you need to understand intimately how DFS works and we can proceed. So I will now pause here for about 10-12 minutes. Take your time. I want you to go through this code, okay, and then we'll discuss this code together. Geek for Geeks, the link is there. Go to the code at the bottom of that link and you will see. Yeah, so we'll wait for about 10 minutes. You can close the video. Okay, let's start. Yeah, so going back to the chat, just open the chat window. Yeah, okay, so I guess we can start looking at the code now. I gave you about 10 minutes time. So let's start looking at the code and let's understand how the code looks and works. Okay, so if you notice, let's go down. Okay, now let's focus on the class graph first, and I am hoping that you will understand, because we are going to use this code extensively both in the finishing school as well as any kind of coding. So you have to get very familiar with the graph. So class graph, it has two data structures which are important. So visible, no? Screen share?
Checking. Yes, it is visible.
So the class graph, it has two data structures which are public, which are important. Now, first data structure is a map. Now, a map is like a dictionary in C++. It's a very good data structure. This is called key and this is called value. What we are saying is for visited, we are keeping a map. Now why do we need a map? Because key will be the vertex indices, all the vertices, like 1, 2, 3, 4. Value will be Boolean, which is this vertex visited or not? So if vertex 1 is visited, we'll say true. Otherwise we'll say false. So that is what is the use of this data structure, int Boolean. Then we have another data structure, which is the adjacency list. This ADJ is the adjacency list. This is another map, again a key value, but here the key is again a vertex, an integer. So key is an vertex, which is an integer, and value here is going to be a list. It is not going to be an atomic value. It is going to be a list of all the neighbors. So these are all the neighbors. So during the creation of the graph, we have to build these two data structures. Visited, of course, is very simple to build. It will build all zeros. Adjacency list will have to be built carefully, which will say that I am adjacent to somebody. So if I give you an edge 2, 3, 2, 3, this is an edge. Okay, this represents an edge. Then we will record it in 2. We will record 3 is my neighbor. In 3 we will record 2 is my neighbor. So both these side we will have to record, and this will be added to that list. So for 2, the neighbor, there will be a list which records its neighbors. To that list, this 3 will be added. Similarly, for 3, there will be a list. So for 2, there will be a list. For 3, there will be a list. And we will add 2, so add 3 to this list if there is an edge from 2 to 3. And for 3 also, in 3's list, where 3 is the key, we'll add this value. So this is what is the map. So this is the map data structure which is there. Okay, so now given that there is a map and there is a visited data structure and there is an adjacency data structure, let's explore now how it is used. So there are going to be 2 methods in this class. One is going to be add edge, which is from this vertex to this vertex, which will update obviously this adjacency list, and there will be a DFS which takes the initial vertex. So V will be the initial vertex from where the DFS starts. DFS traversal can start from any node in the graph. So the V is the node from which it starts, and it will count all the vertices which are reachable from V. Okay, so that is what this thing will do. So now let's go through each method and then let's discuss how the DFS works. It's a fairly simple algorithm to understand and do so that we can easily get it. So let me erase this part, and hopefully you know what is going on here. So let's get into the code for each. Let's go to the code for add edge. Now you know when the code is outside a class, we write it like this. So what will add edge do? Let's understand what add edge is doing. So there is a vertex from V to W. The way, if it's an undirected graph, we'll have to call this twice. One to say this is the vertex source, this is the destination. Again, if it is an undirected graph, you'll have to call it with W and V, because then W will become the source and V will be the destination. So what here it means is this is the source and this is the destination. That is what this represents. So what do? We go to ADJV. So we go to ADJV, and so we go to ADJV. Where is ADJV? ADJ for this vertex. That is, we go to that entry for that source. So we go to that entry for that particular source, and against that entry, remember there is a list in the ADJ table, ADJ map. There is a list here. To that map, that is to this list, we do a pushback. Now pushback is a method which is called on this list. So ADJV is a list, okay, because ADJ of V will lead to this list, and on that list we are doing a pushback of W. So W is getting added here, where V is this thing. So V in the V list, in the list associated with the V vertex, W is added. Okay, so that is what this does. Then okay, so I think this much is clear, and we will move on. Okay, comment it. Okay. Now let's look at the DFS algorithm itself. Okay. And as you can see, it's a pretty simple code. Okay, but only thing is plus plus I. After that, is there something?
No.
No, we'll have to open it in the editor. Okay. If there is something there. Okay. This is better. Okay, we'll go through this. Wow. So you remove the comment. So let's see whether you understand this code. And if you understand it, fantastic. You understood a lot about C++ also.
Yes.
Okay.
It's in the pen only. Pen only.
Okay. So graph DFS, it starts at that vertex V. Okay, it starts the traversal. What does this do? First, remember there is a visited map which you can address like an array. The beauty of a map is you can address it like an array. So visited V is equal to true. So you mark visited V equal to true. Okay. So because this vertex is marked as visited, and you are also displaying that vertex. Okay, you are displaying that vertex. Now, what you are doing is you have gone to a particular vertex. Now look at this. Look at the adjacency thing for this vertex. You have gone to that vertex. Now you are going to work through the list of vertices which are neighbors of this V. Okay, so you visited this V. You marked it as visited because your DFS is starting here. So for that particular vertex, you have started the flow. Now you have to go through this list. This is a list. Remember, list of vertices associated who are neighbors of this V. So in order to go through this list, what do? Use an iterator. How do you create an iterator? What is an iterator? This enables you to loop through a list or a collection. This is the called iterator. It actually becomes a pointer, as you will see. So list int iterator. You are declaring the iterator. This is the declaration of the iterator. Iterator is that which enables you to loop through the entire list. It's a very modern way of looping through a list. Okay. So list int in C++. Java also has iterators, but Java no longer uses iterators. So you just go one by one in Java. Okay. You don't need an iterator. So list int iterator I. So you create an iterator I. So which is like a pointer to a list like this. And now you see how I'm using the iterator, how I'm initializing the iterator. So the iterator starts, or the pointer starts to ADJV. That is, this is the ADJV. V is the slot, the vertex we are looking at. Begin. Begin means ADJV is actually this list, right? The list which I marked here. Begin means I gets position here. Okay, I gets position here. It's a pointer to this element, the first element. I not equal to ADJV end. That is, this is the ADJV end. Okay, this is the begin, this is the end. So for every list, ADJV is a list. For that list, I am positioned at the beginning, and I will go on till I reach the end plus plus I. This will increment the pointer. So every time the pointer will move on. Now, what does it do in the body? It doesn't do much. If it is not visited, star of I. Star of I means that particular vertex. I told you, I will be like a pointer which starts from here and goes till here. ADJV's begin to ADJV's end. It will go from here till here, and it will do plus plus I. And visited star of I means if star of I will give me actually the vertex, which is listed here. If it is not visited, then I will start a DFS with that node. So for example, if you visualize this, and let's say 2 has 2 neighbors, let's say 3 and 7, if these are the neighbors, it will take 3 first and do a DFS on 3. Okay, it will start a DFS on 3. And once it DFS for 3 finishes, which will go to 3, find its neighbors, then go to the neighbors of that and find their neighbors, it will go on. unless DFS 3 is over, it will not do DFS 7. Okay, so that is what it means. So it will do the DFS of 3 and then it will go back, pick up the next element from this list and again do. But this is a recursive code. You see, this is the same DFS which is happening here. Okay, so that is the code which we are doing. Okay. Now let's see how this two functions add edge and graph are called. Okay, so let's look at the driver code for this. Okay, so graph G is instantiated first, which just creates the graph. Then edges are created one after another. So let's see how this graph looks like and how the data structures are going to look like. So you can move up and down at your will. So when you say add edge, what does it do? It says I will create an entry in the map, which is that second map, which is the I don't know what is the second map called. It's called
integer and list.
No, this is integer.
Yes.
No, what is the name of the map? And this is a list. So adjacency list. Sorry.
Yes,
This is called ADJ. Okay. So this adjacency list. So now 0. Okay. 0. And in this list, I'm just denoting the list like this. Okay. 1 will be there. Okay. And so then it's a directed graph. So there is an edge from 0 to 1. Then there is an edge from 0 to 2 also. So 2. Then there is an edge. Okay, that's it. So there is no edge from 0 to anywhere else. So now there is an edge from 1 to 2. I am looking at this 0 to 2. I have already absorbed here. So 1. So entry will be made for 1. 1 to 2 there is an edge. So 1 to 2 there is an edge. This will actually form a list. This list contains 1 and 2. From 1 there is no more edges. So we complete this. Then 2 we have an edge up to 0. So there is an edge to 0. Okay. And also there is an edge from 2 to 3. So 0, comma 3. Okay. This is the list sitting with 2. And then from 3 to 3 again there is an edge. There is a loop kind of thing. So 3 to itself. Okay. So 3. It's called a self loop. So that is what. So now if you start a depth first from 2, how it will go? So this is from 2 to 0 and 3 and then 0 and all that. So how will the depth first go? And we will run it manually first so that you understand it, and then we will do it programmatically to see what it yields. So it will go to 2. Then it will mark 2 visited and display 2. Okay, because it's starting at 2. Then it will look at the neighbors of 2 in this list. Then it will go through each element of the list. Now here I will first point to 0, which is the beginning of this list. Remember, ADJ begin. It will point. I will point here, or whatever variable you want to use, it will point here. 0. So it will do DFS on star of 0. So I is pointing to this 0. So star of 0 is 0. So it will start with 0. 0. What are the vertices available? 1 and 2. So before that it will mark 0 as visited. Then it will do, it will look at the list of 2. Remember, it is not going to 3, it is going to 0, and then it will chase because it depth first. So it will chase this first. So then it will go to, it will find out who is the first guy it is pointing to? 1. It is pointing to 1. So from 1, it will go to 1, and 1 it will mark as visited. So 2 is visited, 0 is visited, 1 is visited. So it goes at 1. Now it finds out who are the neighbors of 1. Okay, it goes here now. So the I will point here, the star of I will point here, or I will be here. So then who is the neighbors of 1? The neighbors of 1, as you can see, is only 2. So it will go to 2 and mark it as visited. No, it will not go to 2 because 2 is already visited, sorry. So this one journey is over. So from 0 it will backtrack. So from here it will go back. The journey of 1 is over because it has reached the end. There are no more nodes to visit. So it will go to 2. 2 is already visited, so it will not go anywhere. So the journey of 0 is over. So where did we start the journey? We started at 2. So 0's journey is over because 1, we have visited everything, we have reached a dead end. 2 also we have reached a dead end because 2 is already visited. So now 0 is over. Now we go to 3. So now remember this thing is still going on. So this is 3. So now it goes to 3. Now once it goes to 3, it will mark 3 as visited. Okay. And it will see 3's neighbor, which is already 3 who has been already visited. So there is nothing more to do. So the output will be, some kind of output will be 2013. As per this code, because it is picking up in this order, it is going to be 2013. Okay. So if you run this code, let's see whether we get that order. Okay. Okay, we'll have to okay, let's run it and see.
Yeah, that's all. Visitor may not be initialized.
Not visited. Showing some other line, no? Test CPP int visited. Visited, where is it created? Semicolon, some semicolon missing. Graph
38 and 4.
Line doesn't have anything. Okay, the output as we can see is 2013, which is what we expected from our code. Okay, now, yeah, so, okay, now let's see whether you are capable of making a change, if you have understood this code. See, yeah, a small change I want to the code is like this. Okay, listen to that change and I'll tell you what we do, what I want you to do. Make a small change to this code, which is like this. Now, so, can we go down? I'll explain what change I want you to do. So, you know what is the adjacency list going to look like for this, right? Where is it? Oh. So, the adjacency list is going to look like this. For 0, the adjacency list is 1 and 2. Okay. For 1, the adjacency list is only 2, correct? Yes. For 2, the adjacency list is 0 and 3, no? 0 and 3. And for 3, the adjacency list is just 3. Okay? This is the adjacency list. Now, in this picture, just to get familiar with this, in this picture, we are always going from, let's say we are starting at 2. So we are examining it in the beginning to end. The list of neighbors is left to right, okay, based on this list. Now, can you make a small change and go from right to left in the adjacency list? Both are depth first search. I can pick any neighbor. Right now the order of picking the neighbors is from first to the last. Now, can you pick the neighbors from the last to the first? I mean here, because of the order, without disturbing this order, that is, this adjacency list will still look like this. can you make a change so that the DFS goes from last neighbor to the first neighbor? Right now it is going from the first neighbor to the last neighbor. It doesn't matter. It is already DFS, so it's going like this. Make it go this way as a, just to see whether you have got a complete grip of the code or at least some grip of the code. Can you make that change? As soon as you make the change, please let us know so that we can look at your code. And not more than 5 minutes, please. It shouldn't take more than 5 minutes to make this change to your code. So we would like to see the change. As soon as you do the change, let us know. Okay. Shouldn't take more than 5 minutes. This is just so that to get you familiar with the code and see whether you are understanding what we are doing. Instead of going left to right, it should go right to left. Small change.
They need to write it. So actually, we haven't given this code.
You haven't given the code? No, they can copy the code, no?
Oh, it's an example.
No, they can't copy the code from Geek for Geeks.
No.
Okay, we'll give you this code.
Actually, we can't see their code even though they change.
No, we will give you this code. Just a minute. Do the change to the code we give. Just hold on for a minute. We'll open a practice lab and give you this code so that you can make changes to this code.
Go practice with it. Turn editing on. Request to find out. ఇంట్లో స్టార్ట్ చేసుకుంటాం స్టార్ట్ చేస్తాం
Copy చేశారా?
Yes, sir. DFS practice labs. The lab name is DFS.
Okay, so you have to make the change to DFS practice lab. We have started a DFS practice lab. Make a change to that so that we go from right to left. Okay, we'll wait for you, at least a few of you to finish. I hope you understood the question. Okay. And then tell us what is the retrieval order that you will see. And that will also be DFS. Okay. So tell us as soon as you are finished. Let me see if everybody should do actually. Can't do even this much, I don't know. We have given you practice lab, DFS practice lab.
Yes, sir.
Please check it and do it. Done. Okay. At least two people finished. Okay. We'll wait for some more. We'll not proceed till at least 10 people finish and we'll check their code one after another. We'll see. Okay, you can print the order when you go from left to right, right to left in the list of neighbors. Okay. Yeah, that looks about right. Yes, correct. Okay, let's see some more. Then we'll pick one or two at random and check. But we are not going to move till at least 10 of you are able to do something. Make the change so that I go through the list of neighbors from not beginning to end, but from end to beginning. And make a change to our DFS lab, DFS practice lab. So far only 2 people have finished. We can't proceed till 10 people have done. Okay, 4 people have done. We just want to go through the list of neighbors in the reverse order. Okay, 1, 2, 3, 4, 5. Okay, so 5 people. We will not proceed till 10 are there. I'm still waiting. I've given you the code under DFS practice lab 5. Yeah, just DFS practice lab, sorry. Only 5. ఎంతమంది చేస్తున్నారు చూడాలి.
58.
Yeah, some 50, 78 are doing. Anyway, let's see if any more have finished. Go to the chat. The same kada.
No,
6.
6.
Okay, 6.
Straight.
I'm just asked a simple question. I want to visit the neighbors rather than from beginning to end of the list, from end to beginning I want to do. Okay, one more guy, 7. Eight. 9. 10. Okay, we are at 10. So let's pick one of them. let's pick not the first one. Let's pick Shreya. Okay. Let's see Shreya's code and let's look at it. So this all remains same. So visited begin to end. Okay, no change. Come down. Come down. If you don't do the change, how will it work? Shreya, you have to change the code.
No, she added a reverse.
Acha, reverse. Oh, sorry. Okay. I didn't see that. Sorry. Yeah. This is correct. If you reverse it, this is correct. Or you can do this way also.
We'll check another.
And to no, this is correct. This is the best way to do. You have to reverse the list. And how do you reverse a list? Is like this. This is a good way of reversing. Good. This is what I was hoping you will do a research and do it. Or you can do another way. You can do a minus I minus minus. You can say this is here and it's not equal to this, and do I minus minus. That is go back. So I was expecting some people to do that also. So this is fine. So yeah. Okay. So let's see someone else. Let's see Nagali Teja. Teja. Okay, he has used R begin to R end. That is also fine. So R begin to R end is also fine. It's a reverse iterator. You have used a reverse iterator. That's also fine. This is fine, perfectly fine. You're starting at the end and going back, plus plus I. Okay, it's a reverse iterator. Good. This is what is called good thinking. Good. Okay, let's move ahead. Let's see one more. Okay. Let's see. Lanka Divakar. So let's see how he is traversing.
Reverse center.
Okay, again a reverse and then take it eventually. Okay, fine. So this is good code. And now, since some of you are doing, some of you are just sleeping, I want to wake up everyone. Okay. Okay. Here is one more to be done. Now this is again to work with the iterator a bit. So given an edge, given a vertex, you have to print who are the vertices adjacent to that very quickly. Okay, I'll explain it. I'll say it again. So if I give a vertex 2, let's say, or whatever. So if I say vertex 0, you should give me who are the neighbors of vertex 0. Don't give me a list. Give me the 1, 2. I mean, assuming that 1 and 2 are the neighbors of 0. So you should tell me who are the neighbors of 1 and 2. Okay. So can you do that? You should tell me, if I give a vertex from the adjacency list, you should tell me who are the neighbors of 1 and 2. Of 0. So what you have to do is, you have to change the code a little bit in the main code. Ask for the vertex. Okay. Ask for the vertex. And then print who are the neighbors of that vertex. You can print in any order, doesn't matter. For a given vertex, who are the neighbors? Okay. So, did you get the question? Yeah. Yeah, you can change whatever. So, oh, it's not working. Maybe it's not allowing, maybe I made a mistake. It's not allowing us to go from minus minus I. Okay. I think it doesn't allow that. If I'm not mistaken, C++ I am mistaken. It only allows you to go in forward direction. So maybe you just have to reverse it or use R begin. Okay. Oh, it worked? Okay. So why is not working for him? Okay, let's see Nikhil's code. Nikhil, you are talking about this question only, no? Not the given a vertex, print its neighbor. Are you talking about that? No, that's fine. No, we are addressing Sriranga's question. Rangamna. We are Sriranga's question, whether we are able, whether we can do I minus minus or not. I think this doesn't work. You have to do reverse and do it, or you have to do R begin and R end to go in the reverse order. Okay. Okay. So, oh, okay. Achha, it's working. Okay, let's check. Let's check. Who is he? Nikhil Kal. Iterator. Position at the end, do I minus minus. Okay, fine. So this is working. So you can start at the end and go back with doing I minus minus. Okay. So is this working? Let's check. Yeah, it's working. Okay, fine. So I take back. It works both ways. You can use reverse, you can use R begin, or you can go backward. Okay. R begin, it just work, no? Check. Okay, now, yeah, it's working. Okay, good, Nikhil. I was a little skeptical. Okay, now get this question, the second question. Given a vertex, print its neighbor from the adjacency list. Print the neighbors from the adjacency list. Done. Okay, good. 1% done. Done. Given a vertex, print its neighbors. Who are the neighbors of a particular vertex? Print them from the adjacency list. It's very easy. Yeah, please finish so that we can proceed. The reason I am spending so much time on this code is basically because you have to get extraordinarily comfortable with DFS code. And similarly, we'll do the same thing with BFS, then we'll do a bit of exercises and check. Okay. Given a vertex, print the neighbors. Any order is fine. Ask for the vertex. Go to the adjacency list associated with that vertex and print. So you might have to change something and do it. Neighbors of a vertex. ఎంతమంది చేశారు చూడు ఇక్కడ కాదు బాబా 2 was done. Only 2. Hey guys, come on. You can't be that bad. 3. Given a vertex, print its neighbors. Take the vertex from the user in the main code and then print its neighbors. Okay. Fourth person. Okay. Okay. Fine. Okay, so let's watch another person, somebody's code. Pick one person. No, Baba, not that guy. Who did the first?
First is Dinesh Reddy.
Dinesh Reddy. Mari, why are you going somewhere? Dinesh Reddy. Okay, let's look at the code. See out, no, this is just printing the vertices one by one, but we don't want this, right? We want you to go to main. No. You ask for the vertex from the user and then print that vertex's neighbor. That is what I want. I don't know why it's so difficult for you to understand some simple stuff. I just want you to ask the user, that is, do a see in, see out. Okay. Okay. Let's look at Lanka Divakar. Okay. So let's see whether he has done it the way you want it. Print list. Okay. Graph, print list, adjacent of.
And whatever.
Okay, print list is go through. Okay, good. Adjacents of people of NR, you go to X, go to adjacency and print. Vendor, go to the adjacency matrix and print. See, you have to do a little bit of research and do. So he is asking it. Where is he calling print list? C in K. Okay, run it. Run it. Your vertices are, so choose 2. Return. Very good. 0 and 3. Okay. That extra arrow can go away, but that's okay. Neighbors of 2 are 0 and 3. Okay. Good. This is what we wanted, Lanka Divakar. Okay. So this is how we want. I was just trying to see whether you know how to access. So given a node, see, this is how it is done. Go to a node and this will be coming as a parameter from the main, and then find out the adjacency list of n. This is the adjacency list of n. That is, from the adjacency list you are going for n, and then you're going through each entry in that adjacency list. This is what it does, and printing it. Okay, good. This is what we wanted. Okay, yeah, you can remove this backslash arrow for the last guy by either putting it in a string and removing the last two characters, or by checking whether you have reached the end and then doing it. Okay. Okay. Okay, here is now something which I will illustrate, but I don't know, this was just to build up for this exercise. Now, I want you to do this interesting work, okay? Let me illustrate DFS with a stack, okay? Let's talk about DFS. So let me erase some part of this. DFS internally uses a stack, but now we are going to try and use a stack in another way. So I'm just rubbing off some of this so as to do this. Okay. So we can use a stack also explicitly. When a function calls another function that is doing recursion, recursion anyway uses a stack. So it is not necessary to explicitly use the stack, but you can do it without recursion using a stack. So DFS without recursion, okay, sorry, without recursion using stack. So here we have called recursion DFS with recursion. We can use this with using stack. Okay, so this code is also there, but I'll show you how it happens. So first you put the first vertex where you want to start on the stack. Okay, 1 on the stack. Then from the adjacency list, find out who are the neighbors of 1. Okay, you will know the neighbors of 1. So pop 1 out and push the neighbors of 1 onto the stack. So the neighbors of 1 will be 2 and 7. Okay, so this is 1 is already printed. So now go for 7 and print 7, pop 7, that is, pop always the top of the stack, pop 7, and then you will get 7 on the output. Then look at the neighbors of 7. Who are the neighbors of 7? There is only one neighbor of 7 which is not visited. Okay, you have to still keep the visited array. Only the DFS algorithm will change. The otherwise graph and all will same. So 7, the unvisited neighbor is 8. So you print 8 and you put push 8 onto the stack, the neighbor. Then you pop, 7 is already popped, so it's not there. So 8 you pop, and then you pop 8. So you get 1, 7, 8. Then push the neighbors of 8. Who are the neighbors of 8? 9 and 10. So now the stack starts looking like 2, 9 and 10. This is how it works. The output is so far 1, 7, 8. So now you pop 10. So when you pop 10, you print 10 there and find out the neighbors of 10 and push them to the stack. So now the stack looks, 10 has been popped, but it looks 11. Again pop 11 and unvisited neighbors of 11 are not there. So done. So 11 gets popped. 9, pop 9. Unvisited neighbors of 9 are not there. So 9. Then you are done with this. Now you continue with 2. And now who are the neighbors of 2? 3 and 4. So you pop 2. So 2 gets popped. And the neighbors of 2 get pushed. So the neighbors of 2 are 3 and 4, which are unvisited yet. Okay. And the story continues. Now I hope you are understanding the difference between what we did using recursive DFS. We are doing it explicitly using a stack. Okay. Now everything else will remain the same. Only thing is your algorithm will change to use a stack of int rather than using recursion, and you will keep popping till stack is empty. So you pop a particular value and initially just push the first guy whose traversal you are going to start, and then keep doing this till your stack is empty. Okay, then you don't need recursion. Okay, now what you are going to do is, okay, I don't expect too many people to do it, but then as I said, KMID always has those what we call the high flyers, who will actually do this. I am making my question very clear. Right now, let's go to the code. Listen to the question correctly, those of you who are able to do and make progress. So if you look at this code, this DFS algorithm is a recursive algorithm. Okay, if you notice, it is going this, printing that, and then it is going through all the neighbors and doing recursion on the neighbors. Now I am saying, don't use recursion. This is a recursion, remember? Don't use recursion, instead use a stack. So in this DFS, use a stack inside it, stack of ints of course. And you know how to create a stack of int, stack int s, and get rid of this recursion. Okay, rest of the code remains same. Visited, all that remains same. I mean, you'll still use visited. Now you implement this code with a stack. Let's see. You have to change this code only, which we have in DFS practice lab. You have to make changes to this code and incorporate a stack for this code. Okay. How do you incorporate a stack? I just showed you. You pop that, push that value. First push the first vertex, go into a loop while stack not empty loop, and then keep popping from the stack and pushing their neighbors. When you pop, print it. Push the neighbors you can get from here. Okay, for a given vertex you always can find out neighbors using this part. Push the neighbors if they are not visited. Okay, if they are visited, forget them. Okay, let's see whether you will be able to make changes to this code. Don't touch the rest of the code, but still just make changes to this code, and I am confident that at least there will be one or two guys here who will do it.
You created another practice lab.
Why change this now? Acha, okay. Okay, we have another practice lab for this, practice lab 10. Okay, with the same code. The starting code is the same. No? Same code, no?
Same code.
Same code ante? Old.
No,
Ready?
Yeah.
sir.
Wait. Please don't do.
Just they need to write the DFS, the DFS part. Main and add edge is same.
Ade,
Avuna same.
go there.
DFS stack practice labs.
It is called DFS stack practice lab. Only thing is, the DFS code will change. Okay.
Instead of recursion.
Instead of recursion.
You have to use a stack inside that.
That's it.
Instead of recursion. Anything which can be done with recursion can be used with a stack in an iterative way. You have to use a loop while stack not empty and do it. This will give you a lot of background on how to use stacks. Don't use recursion. Recursion implicitly is using stack. So we don't want you to use recursion, we want you to use stack.
Iterative.
And make changes to that stack practice. Don't change anything else. Practice lab and make it work with the stack. We have given you the rest of the code except that you have to write DFS. Write it carefully using a stack. No recursion. Oh, very good. Okay, we'll look at your code, Nikhil, in a moment. But at least, as I said, there will always be people who will finish. You don't need recursion if you use a stack. That's a standard rule. Oh, good. Akshit. Okay, it's 5 minutes past 1. At 1:10, we will start discussing the solutions. It in that practice stack question. DFS stack practice.
Names.
Repeated names, same names. Yeah, same people are doing. So, okay, I am seeing the same names coming again and again, which is good and bad. That means all others are just lousy, right?
Only 36 people are trying.
Huh?
36 people are trying.
How many are trying? Go to the screen.
36.
So out of 350 people available, about 10% are trying. 6 people have been able to do. It's horrible. Okay. You must be one of the lousiest batches I've seen actually. Yeah. Okay. So let's just check. Okay. So we will see whoever is the first guy who has done. Nikhil. Okay. Let's look at Nikhil's code and see how it has progressed. Nikhil. Okay, so let's study this code and see how the DFS works. Good. Okay. Okay, let's look at this code. Looks good. Yeah. So stack int A. So you start with this. You create a stack A, and in the stack first push S. Correct. This is how it should be. And then create an iterator on the list or an integer. That's fine. While the stack is not empty, keep doing. Get the topmost value in the stack. This doesn't pop it, I think. We get the topmost value, mark that as true and display it. Good. And then pop it. Wonderful. Then go to all the neighbors of VK, which is the guy who just came off the stack. Go through all the neighbors of VK with the iterator, and if it is not visited, marvelous. I just push him onto the stack. Fantastic. Okay. Push star of I onto the stack. Beautiful. Okay. This is just great. Okay. This is what we wanted. So you see there is no recursion, no nothing. There is no recursion. There is no DFS getting called. It is working using a stack. So stack is empty. Take the topmost, print it. Before that, mark it as true, so you don't keep going back to it. And then you say pop. So it's gone from the stack because top just gives the topmost element. It doesn't pop it. So here we pop it, and then we go through the whole list of neighbors of this and push them onto the stack if they are not visited. Very good. Very good. Okay. So let's see someone else's code whether it follows similar story. Okay, let's see who else. Soma, Akshit, Soma, Akshit. Let's see. This is the second guy to do. We'll look at 2 or 3 code and okay, we are looking at Soma Akshit's code. Again, very similar, looks very similar, which is good. Stack is not empty. Pick up the top guy, pop him, print it, go to mark it as visited, go to the neighbors. If they are not visited, push them. Beautiful. This is also very good.
Use map, sir. Instead of list, use map.
Huh? No, visited is always a map, so it's okay. You don't need it to be marked. It's okay. You can use this map. Or you can use the original map which is there in the code. No, this is fine. Absolutely fine. Okay, very good. Akshit. Okay. At least the guys who are doing it well. That's good. Then who is the third?
Chetan.
Chetan Shintre. Okay. Chetan Shintre. This is the last guy we are going to see. Right there. Okay. Let's go to this. Yeah. Just created a stack. Pushed S. Okay. You have created your own array. Visited V. Boolean false. Very good. Vector. Okay. Empty, pop, not visited. If it is not visited, it won't be visited. Okay, if it is not visited, then see out visited S is true. Because you are checking, you are not visited, you don't have to check again. This may not be this. You don't need to check this. You can straight away output because if it's only not visited, then only you are pushing him on the stack. So that's fine. So this check may not be required, nothing wrong in it. Yeah, perfect. Okay, fine. Sort of fine. Okay, good. Okay, so with that we stop. We have explored DFS, and next session we will do BFS and we'll use the queue. Okay, so
Copied as this from Big Swaggy.
huh?
This guy, Chetan.
Copied. Okay, doesn't matter. At least he knows what to copy. Okay. Okay, fine. So yeah. Anyway, good. So we are coming to an end of today's session. We will meet again on Tuesday, where we'll take up BFS.